Jai Hind to all. Myself PANKAJ GAUTAM, HOD Assistant Professor of EEE Department, Swami Vivekananda Bharati University, Meerut. So my subject of presentation is electromagnetic field theory. So today we will discuss about the introduction of electromagnetics and vector analysis. So what is electromagnetics? Electromagnetics is a branch of physics or electrical engineering in which we study about the electrical and magnetic fields. So electromagnetic principles find applications in various areas such as microwaves, antennas, electrical machines, transmission lines, satellite communications, bioelectromagnetics, nuclear research, fiber optics, electromagnetic interference and compatibility, electromagnetic energy conversion, and meteorology and remote sensing. For designing the electromagnetic devices, we need a complete knowledge of electromagnetic fields so that we can design the electromagnetic devices. What is the field? So field is a special distribution of a quantity. A quantity may be a scalar quantity or vector quantity. So when an event at one place has an effect on the other place, so the effect of the one event of the other place is called as a field. It can be a scalar or vector function. A field is a function that specifies a particular quantity everywhere in a region. So now what is a scalar and vector quantities? Scalar quantity has only magnitudes. For examples are time, mass, distance, temperature, entropy, electric potential and population. These are the scalar quantities examples. And a vector quantity has a magnitude as well as its direction. So examples of the vector quantities are velocity, force, displacement, electric field intensity. In these we need to represent a magnitude value as well as its direction. So to distinguish between a scalar and vector quantity, we need capital letters, and we mark an arrow or caps on a letter to represent a vector field. And for a scalar quantity, we represent just for letters like A, D, U and B. If we represent it's a vector quantity, so we if the quantity is a scalar quantity, then refractive index of a stratified medium. These are the examples of scalar fields. And to gravitational force on a body in space and velocity in raindrops in atmosphere are examples of vector fields. So now next, what is a unit vector? Unit vector represents the direction of particular vector. So a vector has both magnitude and direction. The magnitude A of scalar written as capital A or modulus of A. Particularly the unit vector is along A suffix A. Small a is representing the direction of vector and capital A representing the magnitude of a direction. A unit vector is a vector whose magnitude is always unity, it is 1, and its direction is represented by small a, capital A suffix. So it is a ratio of this vector divided by its magnitude. We can represent further a by a, so its ratio would be the 1. So a vector in a Cartesian coordinate or rectangular coordinates in which x, y, z directions we represent linearly increments. So we can represent its magnitude and vectors. So vector in a Cartesian coordinates or rectangular coordinates can be represented as ax plus ay plus az. So capital A in x, y, z directions are representing the magnitudes in x, y, z direction, and small ax, small ay and small az are the directions of the corresponding coordinates x, y, z. The magnitude can be calculated by squaring and adding by making under root of the all three magnitudes, like under root ax square plus ay square plus az square. This is the magnitude. So we can calculate the unit vector of that field, that is represented by a vector divided by its magnitude. So vector is ax plus ay plus az plus divided by magnitude, that is under root of ax square plus ay square plus az square. This is the graphical representation of Cartesian coordinates in which we linearly doing increments in x direction, y direction and z direction. So these are the ax into ax in x direction, for y direction ay into ay and az into az. So this is the final point where we reach from origin to point P. This is the components of ax, ay and az. So next we need to calculate vectors in addition, subtraction and multiplication for further analysis. So first of all we will discuss about how to do vector addition and subtraction. For addition of two subtraction, let us take two vectors like a and b. So the addition would be the third vector c. So we have taken here two vectors ax plus ay plus az. This is the first vector ax, ay, az in magnitudes of x, y, z direction. And for b vector, that is second vector, bx, by, bz are the magnitudes in the x, y, z directions. For addition, for making addition, we need to draw a parallelogram. This is like b direction, b vector, and this is a vector. So the c vector, which would be the addition of resultant of vector a and b. So in graphical representation, this would be the resultant of a and vector b, which is the addition, which is called the addition of vectors a and b. Similarly, we can explain vector subtraction if we represent a vector a in forward direction, vector b in reverse direction, and we need to add one positive and one negative vector. So we can already represent it as vector subtraction, like a plus minus b, which would be the vector c, which is representing the vector subtraction. Now, what is the position and distance vector? Position vector is a particular vector's location where it is representing, like x, y, z coordinates. So, if we represent a vector in particular x, y, z values at a point, that is called a position vector, and a distance vector is the we can say it is a radius from origin. So the distance vector is represented from the distance from the origin of that particular point is called the distance vector, and at particular point P representing a coordinate system, that is called as position vector. So here like we can take for example 3, 4, 5 at as a point P where x value has 3 units, y has 4 and z has 5 values. So we started from origin to reach 3, 4, 5. So this is the point P where x value has 3, y has 4 and z has 5. So at particular point where x, y, z is defined is called point vector, position vector, positions. We can represent as a vector form like x ax plus y ay plus z az. We can write here 3ax plus 4ay plus 5az to represent as a position vector. And we can calculate also its distance vector. We need to subtract from the final position to the origin value. Origin value like here it is 0, 0, 0. X, y, z, all three values are 0, 0, 0. So we can subtract q point, that is rq. Rq is the position final vector minus rp is the position vector at origin. So if we subtract the final point from the origin point, we can calculate the distance vector. So rpq is the distance vector, which is the subtraction between final to initial point rq minus rp, xq minus xp ax. In x, y, z direction, we can subtract individual magnitudes of x, y, z. So we can get the distance vector. Like here, we can also represent from the origin if a vector is representing p, this is rp vector, and second vector is representing at point q, that is rq vector. So we can calculate the distance vector between p and q by subtracting rp minus rq. Now we can explain some examples regarding position and distance vectors. So here we have given two vectors in Cartesian coordinate systems, vector a and b, like here 10ax minus 4ay plus 6az and b equal to 2ax plus ay. So calculate these three values, component of a along ay, magnitude of 3a minus b, and unit vectors along a and plus 2b. So component of a along ay. So we need to find out the component of vector a along ay. Ay means in y direction what is the magnitude of vector a. So that is the answer. In y direction AY, the component of AY is minus 4. So answer is minus 4. Second one is the magnitude of 3A minus B. 3A minus B means we have to multiply vector A by 3, then we need to subtract 3A minus B. So first of all, A vector is 10 minus 4, 6. We can write here 10 minus 4 or 6, which is understood is it is a magnitudes of x, y, z direction. So we are multiplying by 3. 3 into 10 minus 4, 6 minus 210 are B. 0 means z component is 0. So 30 minus 12, 18 minus 210. After subtraction we get 3A minus B, 28 minus 13 minus 18. Third is a unit vector along A plus 2B. So we need to calculate A plus 2B. So we can write here it is a third letter C vector A plus 2B. By multiplying B by 2 we get 420, and we are adding here A plus 2B equal to 14 minus 2 and 6. So we need to calculate unit vector. So we are representing a third vector divided by its magnitude. So vector is representing here C, that is A plus 2B. Vector is 14 minus 2 and 6 and divided by its magnitude, which is under root of square of 14 square minus 2 square plus 6 square. So we get C unit vector along C direction. C vector. C is A plus 2B, which is 0.913 AX minus 0.13 AY plus 0.3906 AZ. Now, for next example, we have taken 2 points P and Q. 0, 2, 4 it is a P point, minus 3, 1, 5 is a Q point. So we have to calculate the position vector P, and distance vector from P to Q, and distance between P and Q, a vector parallel to PQ with magnitude of 10. So position vector P, we can represent it by RP. So just we write as 0 to 4. This is a P point in vector form of x, y, z direction. So 0 to 4 we can write here 0ax plus 2ay So next example of position and distance vector. So here we have given two vectors, 2 points P and Q located at 0, 2, 4 and minus 3, 1, 5. So we need first point we have to calculate position vector at point P. At point P we have to calculate position vector. So just write this is AX magnitude, this is bi-direction magnitude, and this is 4x magnitude in z direction. So just write in vector form. So 0x plus 2ay plus 4az, which is 2ay plus 4az, which is this is the position vector at point P. Second one is the distance vector from P to Q. So we have to subtract RQ minus RP. So first we also again write Q vector like minus 3ax plus 1ay plus 5az. So we can subtract RQ minus RP. RQ is the final point and RP is the initial point. So a distance vector can be calculated by subtracting final point to the initial point. That is RQ minus RP, P point. So minus 3, 1, 5 is the Q point and 0, 2, 4 is the initial point at P. So we after subtracting we get minus 3, minus 1 and 1. We can also write it as minus 3ax plus minus ay plus az. Okay. So this is the distance vector in vector form, minus 3x minus ay plus az. So next question is the distance between P and Q. The distance between P and Q can be calculated by taking its magnitude. The magnitude can be taken as a squaring of all the magnitudes of x, y, z directions. 3 minus 3 square 9, minus 1 square 1, 1 square 1, that is 3.317. So this is the distance between P and Q. fourth one is a vector parallel to PQ with magnitude of 10. So we just divide its calculate, first of all we just calculate its unit vector by dividing its magnitude to a given vector and multiplying this magnitude 10. We will get its vector parallel to PQ. So here we have done, this is the RPQ is the distance vector P and Q, and divided by mod of RPQ means this is the magnitude of distance vector PQ. So -3, -1, 1 is the this distance vector P and Q, and 3.317 is the distance between P and Q vectors. So we get here unit vector. So after getting unit vector, we can multiply by this value of magnitude 10, which is given in question. We will get final answer. Okay, which is the parallel to the PQ. Now we will discuss about vector multiplication. So vector multiplication are of two types, dot product or cross product. If two vectors multiplication is a scalar quantity, it is called as a scalar dot product, and if the product of two vector quantities is further a vector quantity, then it would be a vector product or cross product. So this is a scalar and vector product representation. A dot B is a dot product, multiplication of two vectors, and this is a cross product, multiplication of two vectors, and further it is also called cross product because its answer is also a vector, and it is a scalar product because its further product is a scalar quantity. So dot product can be written as A dot B equal to AB cos theta. Cos theta AB is the minimum angle between vectors A and B, and in vector form, if A vector is AX, AY and AZ, and B vector is BX, BY and BZ, so we can written as A dot B equal to AX, BX plus AY, BY plus AZ, BZ. Means we have to multiply the same directions vector of all the given vectors AX, BX, which are in X directions magnitudes, plus AY, BY are the Y directions magnitude, and AZ, BZ are the in Z directions magnitude. These are the following laws which are taken as in vector multiplication. A dot B is equal to B dot A in dot product, and this is a cumulative law. Okay. For distributive law, A dot B plus C equal to the A dot B plus A dot C, or we can we can distribute by same vector at twice. A dot A equal to A mod A square, like this. And third also, this A dot product of two unit vectors of similar would be the 1, and others will be the 0. Like AX dot AX equal to AY dot AY equal to AZ dot AZ equal to 1, and AX AY, AY AZ and AZ AX would be the 0. Next. So next is a vector multiplication is cross product. Second type of vector multiplication is cross product. So cross product mein we are taking a parallelogram method. This is the A vector and this is a B vector. So the product of these two vectors would always be in the direction of normal to the plane of that A and B. So the third vector, which is representing the cross product, which is also a third vector. So which is also a third vector will always be the in normal direction or perpendicular direction to the plane of given vectors A and B. So B here represented cross product is equal to AB sin theta AN. This AN is representing the direction of this point. AN is the unit vector which is called the normal vector, normal direction. It means the cross product of vectors A and B will always be the perpendicular to the plane of given vectors A and B. So this is the basic method A cross B. To calculate the cross product of two methods, we have written AX, AY, AZ for mentioning the directions of X, Y, Z directions. We have given vectors A and B. So AX, AY, AZ, BX, BY, BZ. We have written in the matrix form. So we can calculate by taking this chain rule formula. AX equal to AY into BZ minus BY AZ plus BY. While taking AY, we can multiply AX BZ minus AY AX AZ BX, and in case of AZ, we can multiply AX BY minus AY BX. These are the rules for cross product. In case of cross product, A cross B can never be a B cross A. This is not cumulative. So we can say the cross product is not a commutative. It is anti-commutative, because A cross B would always be the negative of A cross B, which is the minus of B cross A. It is not associative. That means A cross B cross C would not equal to A cross B by cross product of C. It is distributed. Distributed means A cross B plus C would be the A cross B plus A cross C, and further A cross A will be the 0. It means ki cross product of same vector will always be 0. And also note that the cross product of two unit directions of AX and AY would be the third direction AZ, and AY AZ would be the AX, AZ AX equal to the AY. Or we can say it is a cyclic rule. Cyclic rules, AX and AY would be the AZ, AY AX will be the AY, and AZ AX will be the AY. If we go to the reverse direction, then we can assign a negative sign of the final value. Next, component of a vector. Component of a vector is a direct application of vector product. Its use in determining the projection. Projection means component of a vector in a given direction. So for a given vector E, B, we can make a component of vector at particular angle theta AB, which is the projection of vector A to the vector B. This is the component of A along vector B. So we can mathematically calculate the projection of vector A along B can be written as A cos theta AB, or we can write as AB equal to A dot AB. So let us take some numerical about components of a vector. So here we have given two vectors A and B. First find the angle between vector A and B. So we can calculate by angle between two vectors by using dot product or by using cross product. So here we have, first of all, we have taken dot product. A dot B equal to 3, 3, 4, 1. This is a 3, 4, 1, and B is a 0, 2, minus 5. 0, 2, minus 5. This is the A vector and B vector. So A dot B, we have multiplied 3 by 0 plus 4 by 2 plus 1 is minus 5. We have got 3 value. This is the A dot B is 3. And individual magnitudes of vector A and B are under 26 and under 29 by squaring and adding x, y, z components. So using dot product formula, we have cos theta AB equal to A dot B, means dot product of two vectors divided by its magnitude. So this is the magnitude, and we will get 0.1092, and taking theta of cos inverse, that value would be the 83.73 degree. Alternatively, we can also calculate by using cross product by calculating theta. In case of cross product, we have the formula is A cross B equal to AB sin theta. So we calculate sin theta AB equal to A cross B divided by individual mod of vectors A and B. So here A cross B have calculated by using this method. We get minus 22, 15 and 6, and this is a magnitude of cross product under root of square A x square B x square c square root 74.5, and by putting the formula of sin theta AB, product divided by magnitude, which is 0.994, and taking the cos inverse, we get 83.73 degree. So the answer will be the same, that is the angle between A and B. We can calculate dot product or by cross product. So that's all for the today.